Example 2.3.5a. In the given circuit, the supply voltage is 1200 at angle 0 volts. Z1 is 60 plus J0, Z2 is 6 plus J12, and Z3 equals 30 minus J30 ohms. Find the power absorbed by each load and the total complex power. The givens in this problem statement are that we have a supply voltage of 1200 at angle 0 degrees volts, and then we know the branch impedances. Z1 is equal to 60 ohms. Z2 is equal to 6 plus J12 ohms. And Z3 is equal to 30 minus J30 ohms. We're asked to find PZ1, PZ2, PZ3, and S total. So, to do this, I'm going to use the fact that the voltage source is in parallel with these three loads, meaning that Z1, Z2, and Z3 all see 1200 at angle 0 degrees across their terminals. I can then calculate their current flow through them and use the formula S is equal to I star V. So that's the method I'm going to use. But first I need I1, I2, and I3. So I1 is going to be equal to 1200 at angle 0 divided by 60 ohms. It's going to be 20 angle 0 amps. Since that first branch is purely resistive, voltage and current have to be in phase. I2 is going to be 1200 at angle 0 divided by 6 plus J12. And that's going to give me an answer of 89.44 at an angle of negative 63.43 degrees. We see that there's a phase shift. Since I've got a little bit of inductance and a little bit of resistance, there's a phase shift between the voltage and the current. And then finally, the last branch current is going to be 1200 angle 0 divided by 30 minus J30. And that's going to give me a value of 28.28 amps at an angle of 45 degrees. So now I've got my branch currents. So just like to, it's not part of the problem statement, but I'd like to point out that the angle of the current is always proportional to the ratio of the reactance and resistance, where the magnitude is always proportional to the magnitude of the impedance. So I could have gotten 20, let's say 89.44. I could have calculated that number 1200 divided by the square root of 6 squared plus 12 squared, right? 1200 over the square root of 6 squared plus 12 squared is equal to, and then I do that and I get 89.44. That's where that part came from. And then the negative 63.43 comes from the opposite of the impedance triangle. So I would have gotten 6 and 12, so I could have found phi is equal to minus the inverse tangent of 12 over 6, would give you negative 63.44, so it's another way to do it. Anyway, we've got these branch currents, so now what we can do is we can calculate the complex power absorbed by each of these loads. complex power in branch 1 is just going to be given by the conjugate of I1 times V1, which is equal to 20 at angle minus 0 times 1200 angle 0 degrees. We get an answer there of 24,000 plus J0 volt amps. So the purely resistive branch has all real power, no reactive power. S2 is going to be equal to I2 star times V2. And that's going to be equal to 89.44 at an angle of 63.43 times 1200 at an angle of 0 degrees. That's going to give me 48,000 watts and 96,000 VARs. Then finally the branch current, or the complex power for the third branch, is going to be I3 star times V3. That's 28.28 at an angle of negative 45 times 1200 at an angle of 0 degrees. That's going to give me 24,000 watts minus 24,000 VARs. Quick sanity check, I had a purely resistive branch. The current and voltage were in phase. I got all real power. I had a resistor in series with an inductor. The current lags the voltage by 63.43. I get 48,000 watts and I get a 96,000 VARs absorbed. In my inductive branch, the current leads in the capacitive branch, the current leads the voltage. I get 24,000 watts absorbed by the resistor and 24,000 VARs delivered by the capacitor in that branch. So all those signs kind of jive with what I would expect there. So I can just underline those right there, and those are the answer to PZ1, PZ2, and PZ3. I can just take the real portion of the complex power calculations, and I will get the powers there. Total complex power is just the addition of all of these. So I just add together S1 plus S2 plus S3. Power is additive in circuits, so I get 24,000 plus 48,000 plus 24,000 is 96,000 watts. And then I got 96,000 minus 24,000, so that's a positive J, 72,000 VARs. And so that gives me 120, if I put that in polar form, 120,000 at an angle of 36.87 degrees volt amps right there. So that's the final answer for total apparent power sourced by the load. I could have also found the total current. If you do that, you're going to come up with a number 100 amps at an angle of negative 36.87 degrees, and then S total is equal to I total complex conjugate times V total. It's going to be 100 at an angle of 36.87 times 1,200 at angle 0 degrees. You can see that that comes out to the exact same number. Another trick that might help you in solving these is that remember that real power is due to resistive portions only, and reactive power is due to reactive portions only. So we'll just take S2 for example. I could have found P2 by taking, sorry, there's some lag in the system right now in the laptop. Anyway, I could have found just P2 by taking the magnitude of I2, squaring that and multiplying it by R. So that would have been 89.44 squared times, I believe in that branch it was 6 ohms. And we find out that that's, rounding, it's 48,000 watts. Q2, that same branch, would have been the magnitude of I2 squared just times whatever the reactance was in that. So that's going to be 89.44 squared again. And if I just multiply that by, in this case, 12, we see that that answer is just going to be twice that one. So that's that 96,000 VARs. So due to the beauty of geometry, you can decompose those into its individual components as long as we just use the magnitudes. So up here we use magnitude and angle times magnitude and angle, and that gave us a complex number. Down here we just used the magnitudes, right? We got rid of those angles, and we decomposed S2 technically down into P2 and Q2, got the same. So it's helpful to be able to switch back and forth and understand that you can use either technique with equal success.